Oh yeah, connect this to your laptop so that adjusts. Okay, nice. Like go on YouTube. And
is it working?
yeah, should be.
How about this mic thing? How does this work? Hello, testing, testing. Okay, this is pretty good.
Yeah. Okay. I'll leave it up to you.
Okay,
I'll check the audio. Yeah.
Wait, can you get this out?
Oh wait. For the back.
Thank you.
Okay. Good luck.
Thanks. Okay, I need full screen. Yeah.
Okay, cool.
Okay, we should begin the stream shortly. You can just scan the attendance form and then, yeah. So just take a moment to scan that. Okay, so I think we're good to start. Okay, so welcome to 2601 Revision Seminar Part 1. We're just going to go through these 6 topics today. And for eigenvalues, we'll go through most of it, excluding SVDs and geometric properties. Those will be in the second seminar. Okay, so we'll start with groups and fields. So first of all, a group is a set G with a binary operation star. So what is a binary operation? It's just an operation which takes in 2 elements of the set and returns another element. That's why binary for 2. And it needs to have these 4 axioms satisfied. So if you want to prove something's a group, you usually have to show these 4 things. First of all, closure. So a group is closed under the operation. A star B is going to be in G as well for any A and B in G. Then there's associativity. So the operation is associative. There's the identity element. So there's an element E. We usually use E for the identity such that A star E equals E star A equals A. So it has the effect of undoing or just not doing anything when you apply the operation to A. Inverses, so for each element there's an inverse, A prime, or you can write A inverse, such that when you apply A and A inverse, you just get the identity back. Then another definition, an abelian group is just a group which has commutativity for the operation as well. So not all groups are going to be abelian, but this just means you can swap the order of A and B in the operation, doesn't really matter. So some examples of groups that we use a lot is general linear group. This is the set of all invertible matrices of size n by n, and it can be over any field, usually R or C or whatever. Some examples are the cyclic group, which is the group of all rotational symmetries of a regular n-gon, the dihedral group, the symmetric group. Okay, these are some important properties of groups. So first of all, a group has a unique identity element, and every element has a unique inverse. These are two pretty common properties. Also, if you apply the inverse, or the inverse of an inverse is the original element, and AB inverse is B inverse A inverse. And also we have a cancellation law or cancellative law, which is just if AB equals AC, you can cancel A from both sides, technically by multiplying or like applying A inverse to both sides. And similarly, if BA equals CA. Okay, we actually have a practice question here. So this time we have a finite group, G. It's an abelian group, which means the operation is commutative. By the way, we can just write the operation as concatenation, or just like, you don't need to write star each time. In this case, we're just going to write it as kind of like how you see multiplication. So the identity is E, and we're defining G as the product of, or the operation of all the elements. Prove that G squared equals E. Okay, so how should we do this? Well, one useful thing is you can write the group in terms of the inverses as well. So A1 inverse, A2 inverse, all the way up to AN inverse, and E, I guess. This is also the group, which is pretty useful. So G squared is A1, A2, up to AN, and then times another copy of that. But because A1 inverse, A2 inverse, all the way up to AN inverse, that's just a permutation of these. So you can actually, for the second copy, you can write it as A1 inverse, A2 inverse, up to AN inverse. And now because the group is abelian, you can reorder everything and it doesn't matter. So you can group these nicely into A1, A1 inverse, A2, A2 inverse, up to AN, AN inverse. And each of these give the identity E. And so you just get G squared equals E. So yeah, this is the formatted solution. Okay, subgroups. So H is a subgroup of G, means H is a subset of G and with the same operation, and H itself is also a group. So there's a subgroup lemma. If you want to prove H is a subgroup of G, you just have to show it's non-empty. And usually that's the same as showing H contains the identity element E. So usually you actually think of it as H contains the identity. And then also you need to prove H is closed under star and inverse. This is what this means. If A and B is in H, then A star B is also in H. And if A is in H, A inverse is in H. So you just need to prove non-empty and closure under the operation and closure under inverses. Okay, there's actually a kind of shortcut for this. Instead, you can just show that, first of all, it's non-empty. Like you still need to show that condition. But for the other two conditions, you can just show it as A star B inverse is in H. Now, this kind of works because you can kind of say like, if you take B, if you replace B with B inverse, then it's kind of showing that B inverse inverse, and then this is A star B is in H. So this is kind of generally, this works to show that it's closed under star. And if you want to show closure under inverses, you can kind of think of taking A equal to the identity E, and then that's essentially showing that B inverse is in H for any B. So this is kind of a shortcut to do both in one go, because it's kind of more general. Okay, definition of a field. So a field it's not a group, but it's a set with two binary operations this time. Usually we call them addition and multiplication, satisfying these two things. F with plus is an abelian group, so it's commutative and it has the group properties. And F is a group with multiplication, excluding 0. And the reason we exclude 0 is because we want inverses to happen, to exist in a group. But if you have a 0 element, that usually doesn't have an inverse. So we just exclude 0, and we want this to be an abelian group. And also this last condition. Okay, so basic properties of fields. You have a cancellation law as long as A is non-zero. This is pretty intuitive. Then A dot 0 or A times 0 is 0. A times minus B is minus AB, where minus is the additive inverse. And if AB equals 0, this is the zero products property. Then A equals 0 or B equals 0. Subfields. So a subfield is just a subset of the field, which is also a field, and over the same operations. Okay, so there's a subfield lemma, but it's kind of annoying. You have to show it's non-empty, and also it's not just the zero field. And it also has to be closed under addition, closed under additive inverses, closed under multiplication, and closed under multiplicative inverses. Okay, so here's an example question. So let F be the field containing just these three numbers. Show that under addition and multiplication mod 12, that this is a field. So to show it's a field, we just need to show F plus is an abelian group and F with times is an abelian group, excluding 0. So first of all, we'll draw this. Now, what I'm doing here is technically showing closure. I'm showing it's closed under plus and closed under times. All you do is you just draw out the table, do 0 plus 0, 4 plus 0, etc., and see if it's still in the set. You can see it's going to be contained. But by the way, this is addition and multiplication mod 12. So it's not your usual addition and multiplication. So 8 plus 8, 16, but mod 12, that would be 4. So that's why we have 4 here. So this shows closure under addition multiplication. It also shows inverses because, for example, the inverse of 4 is going to be 8. The additive inverse is going to be 8 because 4 plus 8 would give 0 mod 12. And this also shows inverses for multiplication. For example, 4, let's see, 4 times 0 is 0. And yeah. So these tables confirm that so these are abelian groups. The next slide will explain this a bit more in detail. So the additive identity is 0 here, as I showed before. Okay, I probably should have mentioned the multiplicative identity isn't actually 0. The multiplicative identity is just where if you multiply A, E, you should get A each time. So it seems to be 4 here because 4 times 0 is 0, 4 times 4 is 4, 4 times 8 is 8 in mod 12. You see 4 is just not doing anything when you multiply it. It just gives back 0 or gives back 4 or gives back 8. So 4 is the identity here for multiplication. And inverses and associativity, commutativity, and distributivity is inherited from mod 12 arithmetic. Okay, group homomorphisms. So this is just a function between two groups, and it's a function which respects the structure of the groups. So you have this property, phi of A star B equals phi of A dot phi of B. What does that mean? Well, A star B is going to be an element in G, and we want this to be phi of A star phi of B, but that doesn't work because H is actually a different operation dot. So we just use the dot operation for H. So that's why the operations change between each one, because the codomain and domain are different. So you need these properties to be a group homomorphism. It's just a function between the groups which preserves the structure. Group isomorphism is just a group homomorphism, so a function like this, except it has to be invertible. So you can go both ways. It's injective, it's surjective, or you can say it has an inverse. And if there is such a function between the two groups, we say they are isomorphic, so they're the same in some sense. And we write it like this. There are some properties of homomorphisms you need to know. Any homomorphism will map the identity of the first group to the identity of the codomain group. So phi of EG is EH. And also it works nicely with inverses. Phi of A inverse equals phi of A inverse. Okay, so so if you have a homomorphism, if you have an isomorphism, the inverse of it is also an isomorphism. And well, the inverse is also going to be invertible, obviously, and you can check it will also be a group homomorphism. Then there's also a notion of the kernel and image of a homomorphism, just like there is for linear maps that we'll get to later. The kernel is the set of all inputs such that phi of g is the identity. So in linear maps, you're used to it being like t of x equals 0. Here it's equals to the identity. So 0 and the identity are kind of like analogous here. The image is just still the set of all outputs, you could say. The set of all phi of g, so that g is in G. Okay, so kernel and image are subgroups of the respective sets. So the kernel is a subgroup of the input space G, the input group, domain group, I guess you can say. And the image of the homomorphism is subgroup of the codomain. So just reminding you, the homomorphism is kind of like a linear map, analogous to a linear map, but for groups. And you also have this nice property. A group homomorphism is injective, so 1-to-1, if and only if the kernel is trivial. So the kernel is just the identity. Okay, we have this example question here. So we have this weird group of matrices. You can assume it's a group. And we're defining H, which is a subgroup. But we're going to, are we going to show? Okay, we're not going to show. But we have a group or a set H, which is a subset of G. It's the set of all X, I guess you can say, which commutes with any A in G, or AX equals XA for all A in G. Prove that X is in H, so this is our set H, if and only if X is of this form. Okay, so X is in H if and only if AX equals XA for all A, right? So we'll only prove one of the directions. Assume this is true, AX equals XA for all A. Now, what is X? We need to kind of write X in terms of G. Like G has given us this basic structure for any element of G. So we'll write X to be something like this, okay? Oh, sorry. So write X to be this. This is just essentially doing, replacing alpha, beta, gamma. We're just using different variable names. Okay, and we'll keep A to be an arbitrary element of the set. We'll say it to be 1, 0, 0, alpha 1, 0, beta, gamma 1, I think, right? Yeah, okay. Now we just need AX equal XA. And if you multiply that out, do AX minus XA, I'll leave the details to you. You actually do get this. And we want this to be 0 because we want X to be in the set. We want AX equals XA. In order for this to be 0, we need this last quantity here to be 0. And this is 0 for all A. So remember the condition. This is not just for N, this is for all arbitrary A. So we actually have freedom to choose the entries of A here. We have mu, we have this. And this is true for all A, which means it's true for all alpha, for all gamma, because that's how we define A. If you want to show that X is of this form, you technically just need to show these ones are 0, right? So we just need to show mu and nu are 0. You could take gamma equal to 1, and you could take alpha equal to 0, and you get mu times 1 minus mu times 0 equals 0, or just mu equals 0. And you can do something similar to just show the other one 0, nu is 0. So that means these two entries must be 0, and X is as claimed here. Since this is if and only if, you'll also have to prove that this X does actually satisfy AX equals XA for all A, but we'll skip that for now. Okay, now prove H is a subgroup of G. Okay, so we already proved, actually we kind of proved that it contains something, it's non-empty. You can show X is in H, right? So to prove it's a subgroup, we've already shown it's non-empty. We just need to show it's closed under the operation multiplication and it's closed under inverses. Or you can show it's closed under X, Y inverse or AB inverse. Okay, so if X is this, now the inverses, you need to try to figure out what is the inverse of a matrix like this. I wouldn't advise actually doing the algorithm for inverses. You can kind of inspect it or use like a, have a hunch what it would be. If you want to know what the inverse of this is, first of all, we're expecting this to be a group. It's going to be some element of the group. So we expect it to have this sort of structure at least. So the inverse should still be like this. And then these last entries, we don't know. Now, you can kind of just guess that it would be something like this, minus lambda. And you can check that this does actually work with the multiplication. So this is actually closed under inverses because this is still an element of H. We showed that all the elements of H are of this form. So then if you do that, if you say Y is 1, 0, 0, 0, 1, 0, mu 0, 1, then XY inverse, you can calculate it, it would be this. And this is also in H because it's still of that same form. It's just all of this and you have some entry here. So this proves that it's closed under XY inverse, which is the same as showing closure under XY and closure under Y inverse. That was one of the properties we went through before. Okay, now define phi of X equals lambda, where lambda is essentially this entry here. So for any X in H, whatever that bottom left entry is, that's what phi is going to be. Now we just need to show it's an isomorphism. So first of all, you need to show it respects the properties of the group. So you need to show phi of xy equals phi of x, phi of y, but you have to be careful on the right-hand side to use the operation of the codomain. So here we're taking the codomain to be this, r plus. So you actually need this to be phi of x plus phi of y. Remember, phi of x is actually a number. It's just a real number here. So we need this to happen. Now, here you can check phi of x, phi of xy. Oh, sorry, you can just say xy. From this calculation here, xy is going to be like 1, 0, 0, 0, 1, 0. I guess lambda plus mu 0, 1. The reason is here we used y inverse, and y inverse had a minus mu in the bottom. But yeah, so here you can see the bottom left entry. You can even calculate it yourself. It will be lambda plus mu, which is the bottom entry of x plus the bottom entry of mu. So you do have this property, phi of xy equals phi of x plus phi of y. Now, that proves that this is a group homomorphism because it respects the operation of the group. Now, you just need to show its isomorphism, which means you need to show it's invertible. You could prove injectivity, surjectivity, but often a nice trick is just to prove it has an inverse by constructing the inverse. So what would the inverse be? It would be from like phi inverse from R to H, takes in a real number and outputs the element of H corresponding to it. So it's actually like a lot simpler than you think. It would just take in lambda and output this matrix here. So you can define phi inverse by phi inverse of lambda equals 1, 1. Is it 1, 1, 1? Yeah, okay. 1, 1, 1, 0, 0, 0, 0, 5, 0. So you can define it like this, and you can check this is the inverse. But you can just check it yourself. It's kind of intuitive. So yeah. Okay, moving on to vector spaces. There are no more groups anymore. We're actually doing in algebra, I guess. So vector space is a space. A vector space is a set of vectors. Now, vectors are just these strange objects which have addition and multiplication defined. Sorry, I should say scalar multiplication. And they have these nice properties. So keep in mind there's scalars on a field and there's objects called vectors. And you can add two vectors or you can multiply a scalar by a vector. And you have these properties. Okay, so some basic lemmas. 0v is 0. Okay, this is technically shouldn't be bold actually. You should say 0v equals the 0 vector v. So here 0 is the scalar and this is the vector. So this actually shouldn't be bold here. It's a mistake. Okay. Lambda times 0 is 0. So if you scale the 0 vector, you still get 0. And then these properties, which are pretty intuitive. I'm not sure, but I wouldn't expect much of this to come up in the exam. Don't quote me on that, but like they have more important stuff to assess, I guess. So subspaces, a subspace is a subset of the vector space, which is also a vector space. And the subspace lemma is, if you want to prove something's a subspace of V, you don't need to prove it's a vector space directly. That takes too much time. You just show it's non-empty. The best way to show non-empty is it contains the 0 vector usually. And you need to show it's closed under linear combinations. So U plus lambda V. In first year, you might have seen like lambda U plus mu V, closure under linear combinations. It's actually for closure under addition and scalar multiplication, but this is actually equivalent. And I'd advise you to use this because it's just easier. You don't need to have two scalars involved. You can just use one. Okay, linear combinations. Okay, so linear combination is just a sum of scalar multiples of the vectors. So if you have v1 up to vn, you scale each of them by certain scalars and add them up. That's what you call a linear combination of them. The span is the set of all of these combinations. And the span of any set is a subspace as well of the vector space. Okay, linear independence. So a set of vectors is linearly independent if and only if the only solution to this is when all the scalars are 0. So the only way to combine them up and get 0 is if the scalars were actually 0 in the first place. Linearly dependent is the direct opposite of this. It means that there's some way to combine them like this, where at least one of the scalars is not 0, and you get this equal to the 0 vector. Okay, if S is a dependent set, we have this property. What does this actually mean? This means you take, it's possible to remove a vector V from the set, and the span is maintained. So if it's an independent set, what actually happens is no matter what you remove, the span actually reduces. If it's a dependent set, it's possible to remove a V from the set, and your span is going to stay the same. Because actually that V would have been a combination of the other vectors. And if it's independent, you have kind of the opposite. If you have a V which is not in the set, but it's in the span, so it's in the span of the set, if you add it to the set again, you're going to get a dependent set. Because if you add V and it's already in the span, it's a combination of the elements of S. This set is going to be independent, this new set. So dependent, it's going to be dependent. Okay, basis. So a basis is a linearly independent spanning set. So it's a set which has those nice properties of linear independence, and it's spanning, which means anything in V is a combination of that basis B. So you can think of B as covering the whole space if you use all the linear combinations. The dimension of a vector space is the size of a basis, the number of vectors in the basis. It turns out that every basis has the same number of elements. So that's why you can define this. Okay, so what's this? Okay, this is just saying you can always reduce a spanning set to a basis. That's not particularly as useful as the next one. This one's really useful in proofs and stuff. This is saying that you can extend an independent set to a basis. So it's possible to add elements to an independent set to make it a basis. So that would keep it independent and also make it spanning. So this is pretty useful. Okay, so if you have a basis, then any combination of that basis is unique. So any v can be written uniquely as this, meaning these scalars are going to be unique for that v. You're not going to be able to find different scalars for that v which still work. So that's pretty nice for, and because it's unique, you can define a coordinate vector thing, which is the coordinate vector of v is just the scalars which give you v. So v is lambda1 v1 plus all the way up to lambda n vn. Lambda1 up to lambda n will be the coordinate vector. Okay, so subspace intersections and sums. So there's some notion of adding to subspaces. What does that really mean? Well, if S plus T are spaces, I know the notation is a bit weird. You usually use T for like a linear map, but here we're using it as a subspace. So just keep that in mind. These are spaces. The subspace sum is the set of all possible sums, S plus T, where S is in S and T is in T. And this also is actually a subspace of V. Okay, so we got a practice question here from one of the past papers. Prove that this is satisfied. Okay, so there's a lot going on. We'll just go through this. So you need to prove any element of the left-hand side is in the right-hand side. So how should I write it? I'll say that W is in X intersect Y plus Z. Okay, and I want to show W is in this thing. Okay, so how would I even prove it's in this thing? I need to prove it's X plus Z and it's also in Y plus Z. So any element of X plus Z is of the form X plus Z, where X is in X and Z is in Z. So can I write W in that form? Well, since W is in this plus this, we can write W equals X plus Z, where X is in this thing and Z is in this thing. Since X is in X intersect Y, that's obviously in X as well. So this is actually in X plus Z. And you can do the same thing for Y. Because X intersect Y, any element of Y would be inside that. So what W we can also write as Y plus Z, and this would be in Y plus Z. And this proves that W is in both X plus Z and Y plus Z. Therefore, it has to actually be in the intersection. Okay, so give an example where the above inclusion is not an equality. So this is kind of the rare question where it's not asking you to prove something, it's not asking you to find something, it's kind of like a counterexample question. So these can actually come up. So how do we find a counterexample to this? Like it's saying when is this not an equality? Here we have a subspace, but they could be equal, right? They could also be equal. They're asking us to find a case where they're just not equal at all. Now, if you want an example of a vector space, the most intuitive space is like R2 or something. That's like pretty obvious. Just try something simple, right? So we'll set V to be R2. And now we need subspaces X, Y, Z of V. One thing to know is the only subspaces of R2 are just like lines through the origin or all of R2. So we want X, Y, Z to probably be lines through the origin. Now, what are some examples? You can do like, well, you can say just like the horizontal line like this. This is the span of like 1, 0, right? So you can say span of 1, 0. And then you can also say span of 0, 1. That would be the vertical line here. This is kind of just like the y-axis. These are two lines through the origin, right? And those would be subspaces. We need another one for z. You could just do like span of 1, 1 or something. Just choose any line that works. Now you can check, will this actually give us what we want? So I'll say x equals this, y equals this, and z equals this. Now let's check what would happen. X intersect y plus z. Okay, so x intersect y plus z. So what is x intersect y? I didn't actually draw the third line, so let's do that. Well, you can see these all have trivial intersection. They only intersect at the origin. So this is actually just the zero space. And I mean, this is actually pretty cool. If you add the zero space to something else, it just gives you z back. because it's the set of all z plus 0, you can imagine. It's still just the set of all z, which is where z is in z. So the left-hand side of that thing is actually just going to be z. And now we just compute the right-hand side, x plus z intersect y plus z. So what is x plus z? It's the set of all x plus z such that x is in 1, 1 and y is in 1, 0. So it's technically you can see it's going to be all of R2 because you can basically get any vector in R2 by just adding these up because they're like independent. This will be a basis for R2. So x plus z is actually going to be the R2 full space. They also said you don't need to give a rigorous proof of that, so you can just inspect that x plus z is going to be R2. So on the right hand side, you get, there's a lot of stuff going on here. On the right hand side, you get R2 for this. And similarly, y plus z, you can show it's also R2. And on the left, we just have z. So R2 intersect R2 is still R2. So we get z is a subset of R2, but z is not equal to R2, right? It's just one line. So this is actually an example where we don't have an equality. We have a strict subspace. So I guess the trick here is just like a classic example is 3 lines in R2. And R2 is like the most intuitive vector space you can think of. So that works. Okay, yeah. Okay, I'll sneakily leave this one as an exercise. You guys can see the slides later, we'll upload them, and also this is live streamed. So yeah, okay. Okay, so dimension of a sum is, okay, this is pretty cool. The dimension of a sum is the sum of the dimensions minus the dimension of the intersection. This is kind of like inclusion and exclusion if you've done probability or combinatorics. It's kind of somehow related to that. It's like probability of A union B, for example, is the probability of A plus the probability of B. You don't need to know this, I'm just like saying. Similarly, the dimension of a sum is the sum of the dimensions minus the dimension of the intersection. You don't need to know about probability unless you're doing 2901, but I'm just saying. Okay, so there's also a notion of a direct sum. A direct sum is still just the sum of subspaces, but you have another condition where the intersection of the spaces is trivial. But technically, the actual definition is the representation is unique, which means any vector in the sum has a unique representation s plus t. So this s is going to be unique for v. You can't find any other s for v which works. Similarly for t. If it's a direct sum, meaning if it has this unique property, we just write it with the O plus symbol here instead of plus. But it's still the same space. It's just same notation. It's just kind of like an indication telling you, wait a minute, this is a direct sum. So still s plus t, but yeah, this circle is just like an extra note that it's a direct sum, meaning everything's unique. But usually the way you prove direct sum for two spaces is you show the intersection is trivial. So that's actually, you can show it's equivalent to a unique representation. So if you want to show a sum is direct, you just need to show S intersect T is the trivial space. Okay, so hey, what is this? Okay, if S is a complementary subspace. So this basically says if you have a subspace of V, you can actually find some other subspace T such that S direct sum T is the full space. You can think of it kind of as a complement, right? Like in set theory, A complement and A, the union is the full space, right? Sum and direct sum are kind of related to unions, like analogous, you can say. We call this complementary subspace, but in this case, it's actually not unique. For set theory, I guess it would be unique, right? A complement is just a complement. But here, there's not actually a unique complement. There is an orthogonal complement, which we'll go through later. Okay, so we have a practice question here. I think this was similar to the one we saw before. Okay, anyway, AX equals XA. And V here is the set of all just 2 by 2 matrices. Okay, prove that it's not possible to find two distinct matrices A and B such that V equals WA O plus WB. Okay, what even is WA? It's the set of all X which commutes with A, meaning AX equals XA. and WB is the set of all x such that, I guess, bx equals xb. Now, why can we not write phi as a direct sum of these? Well, the easiest condition for direct sum is the trivial thing. Remember, the intersection has to be trivial. First of all, is it actually true? Like, is the intersection trivial here? If it's not, then this is not going to be a direct sum. So the intersection of these is all x such that bx equals xb and ax equals xa. Now, when I say trivial, we mean the zero element of this. The zero element of V, the set of all matrices, 2 by 2 matrices, is just the zero matrix. So we need this to be the zero matrix here, where this is the zero matrix. But can you find something in the intersection which is not the zero matrix? Some x such that bx equals xb and ax equals xa. Well, the other like famous matrix, I guess, is the identity. If you take x to be the identity, then clearly bi equals ib, ai equals ia. So I, the identity matrix, 2 by 2 identity matrix, is an example of a non-zero matrix in the intersection, which proves the intersection is not just the zero matrix. So you can't actually even have this because the intersection is not trivial. Okay, linear maps. Okay, so a linear transformation is a function between the two vector spaces of the same field. And they have this nice property, which is essentially it preserves linear combinations. So usually you can write it like this. Equivalently, you can say T of like, okay, I'll just do lambda u plus mu v equals lambda T of u plus mu T of v for all scalars lambda mu. But honestly, this one's better because you only have to use one scalar. It's actually equivalent. So I'd advise using this one if you want to prove it's a linear map. All you have to prove is it satisfies this property. So it preserves linear combinations. And the set of all linear maps from V to W is this L, this weird L of VW. It turns out this space is also a vector space, which is weird because the elements of this are actually functions or linear maps, but it's also a vector space where scalar multiplication is like lambda times T is another function where you just lambda T of V is lambda of T of V times T of V. And addition of the maps is defined like this. It's pretty simple. One thing to note is if V and W are finite dimensional, the dimension of this, remember this is a space, L of VW. The dimension of the space is actually dim V, dim W. So this is actually pretty useful to know. This only works if it's finite dimensional, but I guess it also works if it's infinite dimensional. Infinity times infinity is infinity, but that's not really worth noting, I guess. Okay, so some useful properties. This one's really good. T of 0 equals 0. A linear map will always map 0 to 0. T of minus v equals minus T of v, etc. The inverse of a linear map is also linear, and composition of linear maps is linear. And this last one is more useful when you talk about matrices, like GL n of f is the set of all n by n matrices which are invertible. So I guess think of it more like that. That's usually more commonly shows up. Kernel and image. So just like for groups, we have it for linear maps. The kernel is the set of all inputs such that T of v equals 0. Just like a polynomial has roots, you can kind of think of it as the roots of a linear map, like intuitively. The image is the set of all outputs of the linear map, the set of all T of v such that v is in v. Now, since the outputs are contained in the codomain W, image of T is a subspace of W, kernel of T is a subspace of V because the kernel is the set of all inputs such that this happens. It's going to be in the input space V. So just keep that in mind. And these are subspaces. The image of a subset or subspace, this was defined in like 1081, but it's just the set of all T of U such that U is in U. So this is sometimes useful to know. It's just a notation. You're applying a function to a set, which might seem weird, but that just gives you another set where it's the set of all outputs of the function, where the input is from U. And this also is going to be a subspace. Okay, rank nullity. So nullity is the dimension of the kernel, rank is the dimension of the image, and you have the rank nullity theorem, which for finite dimensional, the dimension of the input space is the rank plus the nullity. Always remember it's the dimension of the input space, so not the output space, W, dimension of V, dimension of the domain, you can say. Okay, isomorphisms, I don't know how important this is, but we'll just go through it. You can actually have an isomorphism between two vector spaces, and that's just a linear map which is invertible. So for groups, we went through like a group isomorphism, which is a group homomorphism which is invertible. Here we have a linear map which is invertible, and it goes between the two spaces. If you have something like that, then you say the spaces are isomorphic, which means they're the same in some sense. And it turns out that as long as the dimensions are the same for V and W, there is actually an isomorphism between them, and they are also isomorphic. So this is actually pretty useful. So yeah. Okay, so linear maps from matrices. Yeah, any matrix is technically a linear map, and any linear map has a matrix with respect to bases. Yeah, I don't know how much this will come up, but like I usually use image of A for the column space of A. You can use col of A because I think the course has used this. Col of A is the span of all the columns of A. So if the columns are like 1, 0, 3, 4 or something, the image is like span of just 1, 0, 3, 4. Or you can say col of A, but yeah. Row of A, this is not much used, but it's the span of the rows. Okay, this question again. So T of x equals xa minus ax. This is a function from, or linear map from the space of all 2 by 2 matrices to the space of all 2 by 2 matrices. They're asking why is this not a isomorphism? Why can this never be an isomorphism? Even if for any a that you take, which is fixed. So, I mean, we could try to show it's not linear, but it might be easier to show it's not invertible. So we could show it's not injective. Invertible means injective and surjective. And one way to show it's not injective is to show that the kernel is not trivial. So there's some x such that T of x is the zero matrix, but x is not the zero matrix. That will prove it's not invertible. So, like, okay, this is similar to that previous example. You can take x to be the identity because IA minus AI is 0. A minus A is 0. But x, or x equals I is not 0. So you have T of the identity matrix, which is not 0, is 0, but I is not 0. Therefore, this is not injective. It can't even be invertible. Okay, we got this actual killer question from MATH2099. Like this is actually like crazy. So using the fact that this is a basis for P2OR, find the rank of this matrix. I would expect this to be a bit scaffolded if we got something like this, but let's just go through it. So how on earth is this even related? You have P2 of R, which is the set of all polynomials degree at most 2. So quadratic polynomials and lower versions. How is that even related to the rank of a matrix? Well, these are quadratics, right? Can you see anything related to quadratics here? Well, the entries are kind of like squares, right? You can say they're like quadratics evaluated at something. If you look at this column, you can see that aij equals like j plus I minus 1 squared. So the first row, where I equals 1, you can see you'll get j plus 0 squared, and you can check this for yourself. The entries are of this form, which is kind of like a quadratic in j and I, right? Maybe you can write it in terms of t and write it as an evaluation of a quadratic, because we want to try to use this fact. So we're going to do, I think, t plus, was it j minus 1 squared, evaluated at t equals I. So all the entries are like that. Now, what's the point of this? Well, we know this is a basis for P2 of R, which means any quadratic in T can be written as some combination of these vectors. So we can write T plus J minus 1 squared as, say, A naught T squared plus A1 t plus 1 squared plus a2 t plus 2 squared. Okay. Now, what do we know about these scalars? They don't actually depend on t, because in the set of polynomials, the scalars are not going to depend on t. They're just actual scalars. They would, I guess, depend on j minus 1 here. So, okay, technically I can say a0j. I'm just going to write it like this to indicate that a0j depends on j. Okay, it's just a scalar, but yeah. Now, how is this going to help us find the rank? One way to find the rank is, okay, let's just think about a small case like a rank 1 matrix. If the rank is 1, that means all the columns are a multiple of some fixed vector, right? So imagine all the columns were a multiple of the vector 1, 0, 0, 0, whatever. Then the rank would be 1. In general, if you want to prove the rank is R, so R could be anything, you could show that all the columns are in the span of some fixed R vectors. So if you can show all the columns are in the span of like some fixed R vectors, some actual known vectors in terms of scalars, then all the columns are in the span of those. So the rank would be at most R. If those R vectors are independent, then the rank has to be R. So we're going to try to write this column as a span of some other columns, or a span of some fixed vectors. So here we already have something like that. We have the first entry is a combination of these things. And if we just repeat this and sub in t equals I for each I, you'll get this. So this is what I did. I just subbed in I equals 1 here, I equals 2, all the way up to I equals 3. You can check this for yourself. But now notice that, can we write the column? The column here is just all the entries of this. Can we write that as a combination of some vectors? Well, notice that these scalars are all the same. They only depend on j, they don't depend on I. So yeah, you can technically make 3 vectors out of this. You get these vectors, 1 squared, 2 squared, up to 100 squared, and then these other 2. And this proves that j squared all the way up to j plus 99 squared, which is an arbitrary column of the matrix, is in the span of these 3 constant vectors. These don't depend on j or I or anything, they're just normal vectors. And you can check these are going to be independent. And what that means is every column is in the span of 3 specific columns, 3 specific vectors. So the rank is actually 3. You can check they're independent, which ensures the rank is exactly 3. But yeah, it's just a weird trick, like showing the rank is 3 is the same as showing all the columns are in the span of these 3 specific vectors. And they also have to be independent for the rank to be exactly 3. Okay, matrix representation. So any linear map has a representation in terms of a matrix. Txc equals Axb. I don't know, I just kind of remember it like this, like it has a nice ring to it. Txc equals Axb. I don't know. But that just means where you take t of any input x, take the coordinate vector with respect to c, which is a basis in the codomain, and it will be a matrix A, which is just a normal matrix, times the coordinate vector of x with respect to b. Keep in mind, coordinate vectors are literally just vectors of Rn or Rm. They're just normal vectors like that. This is why this even makes sense. If the space is some weird space, like you can't just multiply a matrix by a vector. If the space is a weird space like that, then you convert it to coordinate vectors, and that's how you can have this equality. Okay. Then there's this idea of a transformation matrix. This matrix A has a nice form. If you have a basis V1 up to Vn, or okay, I don't know why we're using Q. Okay, P by Q. Then TBC is just T of each basis vector here, and you take the coordinate vector of that with respect to the codomain's basis. So if you want TBC, which just means you're using the basis B in the domain, you're using the basis C in the codomain. So you write B on the top and then C on the bottom, and then it will be this. So this is the thing, TVC equals, this is like A, AVB, or TXC equals AXB. Okay, change of basis. So yeah, so there's this, what does this mean? ID here is just the identity map. So it's the map such that T of X equals X for all X. The identity map just does nothing to the input. And we have this property. This one's actually pretty useful. The identity map where the domain, like the domain basis is C and the codomain basis is B, is inverse of this. And if T is invertible, the inverse is just the inverse of this matrix. You have to make sure to switch the domain and codomain. But yeah, this is the main formula. This is pretty useful to know. I'm just going to look at this. The way I remember it is like, I just imagine drawing like a line cancelling these C and this C out. And what remains is B and D. I don't know if that helps. It's just like a way for me to remember it. So whenever I see this, I just imagine cancelling out these and you get BD, and the input matrix becomes the composition, or the input map becomes the composition. So this is the ultimate change of basis formula. You can see that these cancel, giving you CS, and these cancel, giving you BC. Like, just intuitively, this is not like an actual mathematical thing. And you get C on the bottom, B on the top. This was like used in one of the class tests. So like, okay, now we have a practice question. So we have V is the set of all polynomials of degree at most 1. So these are like linear polynomials, ax plus b. The space, oh yeah, okay. And we're defining this weird map from V to R. So it takes in an element of takes in a polynomial, outputs a real number, which is a bit weird. Tx of the polynomial is the polynomial evaluated at x. So it also depends on this x thing here. Okay. Now, this is actually a linear functional. Okay, it's a covector. We'll go through that later, but it wasn't the course. Covector is just a function from V to the field R. So here the field is R. If it was C, then it would be a function from V to C. Sorry, it has to be a linear map as well. So we call that space V star, which is the set of all linear maps from V to R. And by the way, what's the dimension of V star? Well, if you remember, the dimension of the set of all linear maps from something to something is the dimension of V times the dimension of R. Dimension of R might seem a bit weird, but technically this is like R1. Just like you have R2, this is R1, and the dimension of R1 would be 1. So this is actually the same dimension as V. It turns out they're actually isomorphic. So yeah, by the way, if V is P1 of R, then dimension of V is 2. This is pretty important to note. So if you want to prove this is a basis for V star, you need to show it's independent and spanning, but V star has dimension 2 because it's the same dimension as V. So all you actually need to do is to show it's independent, because if you have it as independent and it's the same number of vectors as the dimension, it will be a basis. So we just showed T0, T1 is independent, which is a bit weird because these are functions, so you might not be used to this. How do you show the functions are independent? Well, you assume that a T0, let's use lambda. You assume that lambda T0 plus mu T1 equals the 0 map. Now these are functions, so what this actually means is lambda T0 of any p plus mu T1 of any p is the 0 map at any p, which is actually still going to be 0. Now, because we know that P comes from this polynomial space, it's useful to write P as like P of T equals AT plus B. This will probably come in handy whenever you have a polynomial space like this. You can write it as like this. This is dimension 2, the space of all polynomials of degree at most 1. You can write it as AT plus B. So for any A and B, this is like T0 of AT plus B. Now, what is T0 of AT plus B? It's the polynomial evaluated at 0. Remember this thing here? So if you evaluate this at t equals 0, you get b, I guess. If you evaluate it at 1, you get a plus b. So this should be true for all a and b. we want to show these scalars lambda and mu are 0, because that would prove that it's independent. So because we have freedom to choose a and b how we want, we can take like b equals 1, so this doesn't even matter, and then I guess you can take a plus b equal to 0. So I guess a equals -1 or something, and then you get lambda equals 0. Similarly, you can show mu equals 0, because you have this freedom to choose a and b to be whatever, and you'll get mu equals 0, proving they're independent. Find the coordinate vector of T2 in the basis. Okay, so what even is T2? I think it was the map such that T2 of P equals P evaluated at 2. So I guess T2 of any, like AT plus B, if you want, is 2A plus B. Now, how do we find the coordinate vector of T2 in the basis B? Well, first of all, T2 is an element of the V star. It's some combination lambda T1 plus mu T0. Let's drop this out. So we just need to find what these lambda and mu are. Like, these are functions, by the way, so you want to evaluate them at something to understand them. T2 of any a plus b should be lambda T1, sorry, this is actually at plus b, because I'm evaluating at a polynomial. At plus b plus mu at plus b T0. T2 of this is 2a plus b, right? T1 is a plus b, and this one was just b, I think. So we want to find lambda and mu such that this holds for all a and b. So now we don't, technically we can't like choose a and b to be anything. This is for any arbitrary a and b. We need to find lambda and mu such that this works. You can technically just take the coefficients. So lambda a plus mu b. I guess lambda equals 2. And just by matching these, and lambda plus mu should be 1. So mu equals 1 minus 1. Okay, so I need to be careful about the order. It says use the order of the basis as given. So technically T0 was actually before. So I guess I should have written T0 at first, but the coordinate vector would actually be what? -1, 2? I think so. Because yeah, mu equals -1 and lambda is 2. Okay, similarity. Two matrices are similar if and only if you can write it as, but this is, I usually write it as P inverse. You can also write it as P inverse AP, but A equals P inverse means A and B are similar. Sometimes you might see them write A similar to B with this tilde. I think that's fine. I think that's allowed. Yeah, two matrices are similar if and only if they're both transformation matrices of a linear map. But what that also means is if you have a linear map, then T BC, or I can say B1 C1, is going to be similar to any T B2 C2. So any transformation matrix of a linear map is actually similar to any other transformation matrix. The reason is, if you remember change of basis, you get some sort of PBP inverse sort of thing from that. Similarity invariance. Okay, these are pretty important. Determinant, trace, rank, nullity, characteristic polynomial eigenvalues. These are all similarity invariants, which just means that if two matrices are similar, they will have these two same properties. That's why we call them similar, because they have a lot of things in common. So determinant, trace. Trace is the sum of the, I think we haven't defined it in the seminar yet, but trace is the sum of the eigenvalues. It's also the sum of the diagonal elements if you're talking about a matrix. Determinant, okay, you guys know determinant. Rank, nullity, yeah. This is actually pretty cool, characteristic polynomial, which means the eigenvalues are all the same and the multiplicities are all the same as well, algebraic. Okay, I will skip this one because it's actually not too hard. Prove that two matrices are similar if and only if these are similar for every lambda. Okay, I'll skip this one for now. But you can note this one down and try it later. Inner product spaces. Okay. Okay, I'm gonna pretend I'm a lecturer and give you guys like a 2-minute break or something, because I need to drink water. Okay, probably wasn't 2 minutes, but like, okay, we'll continue now. Inner product spaces. So an inner product is a function which takes in two vectors and outputs a scalar. So it's kind of a way of measuring the two vectors in a certain way. So it has these properties: positive definite, which means V in a product V is always a real number. It's always a non-negative real number. So the reason I'm specifying it's a real number is because the field could be complex. By the way, something important to note is when we're talking about inner product spaces, in this course, we always assume the field is either R or C, because otherwise it gets a bit difficult if we're talking about finite fields or something. So just keep in mind the field is going to be R or C. So positive definite, V in a product V is always real and non-negative. It's equal to 0 if and only if V is 0. You can even define a norm by norm of V is square root of V in a product V. So you can think of that as kind of like a magnitude of V. Conjugate symmetry. If it's a real inner product space, this is actually same as symmetry because the conjugate of a real number is a real number. That's a pretty useful thing to know. If it's a real space, the inner product is symmetric. But be careful if it's not a real space, if it's in complex, then it's going to be conjugate symmetric. Linearity in the second argument. This is the sort of thing you have to be careful about. It's not actually linear in both arguments, only linear in the second argument by our convention. Technically, it is conjugate linear in the first argument, which it's kind of like a property of this. It's not a definition, it follows from the definitions. Conjugate linearity in the second argument. What does that even mean? It's just normal linearity, but the scalars become conjugated. So if you have u plus lambda v in the first argument, the lambda, when you take it out, it's going to be conjugated. If you're using lambda to be like a real number, like 1, -1, 0, half, whatever, you don't need to worry about this. It will literally just be linear. So if you have like u plus vw, this will be what? uw plus vw, right? You don't even need to worry about conjugating if the scalar lambda is real. Then these other properties, inner product is 0, the inner product of 0 with v is 0. And if you have uv inner product is 0 for all u, so u here is varying and v is fixed, this actually means that v is 0. And literally the way you prove it is, since u can be anything, we take it to be equal to v. And norm of v squared, or yeah, this is norm of v squared. But this implies that v is 0 by positive definiteness. Orthogonality. So you have an orthogonal set of vectors. What does that mean? It means that they're pairwise orthogonal, which means that if you take any two distinct vectors from the set and you take the inner product, you'll get 0. So I said distinct, by the way. If you take the inner product with itself, that's not going to be 0 in general. Orthonormal set is really useful. It's just an orthogonal set, except every vector is unit length. So it has magnitude 1. And you can write it like this. You might not have seen this before, but it's pretty useful. It's called Kroneker's delta. It's just a handy way of writing this thing. It's 1 if both indices are the same, and if the indices are different, you get 0. So how does this work? Well, the set is orthogonal. So what that means is any distinct ones, vi in a product vj should be 0. Distinct meaning I not equal to j. That's what happens here. And if I equals j, you get 1, which is the unit length. So vi, like you can think of it as normal vi squared. This should be 1. So that's where the Kroneker's delta thing comes from. I mean, comes into play, I guess. Unit magnitude orthogonal. So you need to prove both of those. Okay. Useful property is an orthogonal set of non-zero vectors is linearly independent. Why are we specifying non-zero? Because if you have 0 as a vector in the set, it can't be linearly independent. It has to be dependent. So as long as none of these are 0, then this is independent. The proof is you just assume this is the linearly independence condition, and you want to prove all the scalars are 0. The only thing you know about the set is it's orthogonal. So you probably want to use the fact it's orthogonal, meaning you want to take inner products. And if you do that, for example, just with V1, take the inner product with V1, all the other ones will vanish because V1 inner product to V2 is 0, V1 inner product to V3 is 0, etc. The only thing remaining in the sum will be lambda 1 V1 V1 equals 0. And the norm of V1 squared is not 0 because we're assuming V1 is not a 0 vector. So lambda 1 is 0. You can do that for all of them. Orthonormal sets are also independent. Yeah, so this works. You don't even need to assume non-zero because orthonormal means they're all unit length. They can't even be 0. Okay, now we got like actual like difficult question kind of. So suppose VC is in a product space. This just means the field is C. And the vectors satisfy this weird property for all scalars AI in C. Show that this set of vectors E1 up to En is orthonormal. Okay, so how do you show orthonormal? You show their orthogonal first, and or you can show they also have to show their unit length. So maybe we'll do unit length first. That might be easier. So we need to show norm of E I squared equals 1 for all I. We have a lot of vectors here. We don't just have any. We don't just have EI. We have E1, E1, E2, all the way up to En. We want to simplify it. We can take all the AIs to be 0, except I guess I. I think I'll just do it for 1, E1, and then it follows for all the other ones similarly. So take A2 equals A3 equals 0. This is the other trick where you have freedom to choose the variables. You choose them nicely. And take A1 equals 1. Then the only thing remains is E1 squared. And on the right side, you get a bunch of 0 squareds, but you only have 1 squared here plus this. So norm of E1 is 1. You can do this for all the other ones to show that they're all unit length. So that's good. We've showed unit length. Unfortunately, the hard part is actually showing orthogonal. So I think what I'll do is I'll just show E1 and E2 are orthogonal. In general, you can do it for any EI and EJ. But just for simplicity here, I'll show this. Now, E1 and E2, how do we isolate them here? We don't want to focus on any of the other vectors. So at least we should take A3 equals A4, all of this to be 0. I only want to think about E1 and E2. So we're left with A1, E1 plus A2, E2, okay, squared equals, I guess, this squared plus this squared. All the other terms should be 0. Now, somehow we need to show they're orthogonal. Well, we want to take A1 and E2 to be something nice. I guess you could even just take A1 and A2 to be 1. So then you get this. Okay, and let's see, do I have this here? Okay, so then one important thing to note is you can expand this. The norm squared is the inner product with itself. So you have this here. I have space. Okay. Let's rub this out. When you expand this out here, you'll get norm E1 squared plus E2 inner product E1 plus E1 inner product E2 plus norm of E2 squared equals to 2. We already proved their unit length. So norm of E1 squared is 1, norm of E2 squared is 2. So you get 2 on both sides, we can cancel them. And now look, we have something in terms of the inner products of E1 and E2. Notice how the order is switched. Technically, one of these is the conjugate of the other by conjugate symmetry. So you have like, using the fact z plus z conjugate is twice the real part, you can show twice the real part of this is 0, or just like the real part of E1, E2 inner product is 0. We're almost done, right? We've showed the real part is 0. We want to show it's like actually 0. Keep in mind this is complex in general. So you need to show the imaginary part is also 0. Now, if you try taking, like, we're in a complex space, you might not get very far just by taking A1, A2 to be like real numbers, 1, -1. We'll try to use I. We are in a complex space after all. If you take A1 equals to I, where is it? Okay, this one is in general for J and K, but if you take one of the scalars to be I and the other one to be 1, you can expand it out and you get this. Now, this time we actually get a negative sign. By the way, this comes from, I'll just go into this a bit more detail. Technically, you can say this is like IZ minus IZ bar, where Z is this thing. And if you factor out, one important thing from complex numbers is Z minus Z bar is 2I, imaginary part of Z. And so you can cancel the I from both sides, but what you get essentially is the imaginary part of this is also 0. And therefore, real and imaginary parts are both 0, so it's 0. And the set is orthonormal because we've shown E1 and E2 are orthogonal, and we can repeat this for any EJ and EK. So I think maybe the showing the real part is 0 was not too bad. Showing the imaginary part of 0 needed that sort of motivation of taking the scalar to be I, taking the other one to be 1 or whatever. Keep in mind you are in a complex space. You're not going to get too far just by using real numbers. Okay, projection. So the projection of x onto y, this is important because there's a like actual order of the vectors here. Y in a product x over y in a product y, y. So you can't say it's this unless it's a real space. So just keep in mind, like, you probably put this on your cheat sheet just in case. This is not equal in general. You have to have y first. One way to remember it is if you look at it left to right, y actually appears first as you go left to right. Similarly, y will appear first in the inner product. Okay, this one is really important. X minus the projection of x onto y is perpendicular to y. So notice the x, this and this have to be the same. And then whatever this quantity is will be orthogonal to this thing you're projecting onto. So like an example in like R2 or whatever, this blue vector here is the projection. And notice that, okay, I'll call this x. Notice x minus the projection is actually going to be, you can check it yourself, but from vectors, it will be like this vector, this pink vector. Notice that the pink vector is actually orthogonal to this black one, y here. So x minus the projection is orthogonal to y. Okay, yeah, this is important. So coefficients in an orthonormal basis. If you have an orthonormal basis or an orthogonal basis, and you want to write something in the span of that, the coefficients actually have a nice form. Like the coefficients are determined in terms of inner products. This is the like more easier formula. If it's actually an orthonormal basis or orthonormal set, then x is obviously some linear combination of these, right? Because it's a basis, but those scalars are actually have a form. They're the inner product with each basis vector with x. So I'll just zoom into this. Yeah, so this is kind of useful. Whenever you have an orthonormal basis, you can write the scalars of x in terms of inner products. So this is kind of useful. Okay, Gram-Schmidt. So yeah, so every finite dimensional inner product space has an orthonormal basis. This is what Gram-Schmidt is. Basically, whenever you have an independent set or just a basis, you can transform it to an orthonormal basis, meaning it's orthogonal and unit length, everything's unit length. This was in one of the tests, but like the process is you form these vectors w1 up to wn. First one is chill, you just use the first vector v1. Second one is V2 minus the projection of V2 onto W1. Keep in mind, this is going to be orthogonal to W1 by the diagram I showed you. So you do get orthogonal basis for the first two at least. And you kind of repeat this, like, might as well write this down on the cheat sheet if you forget. But this will give you all of these to be orthogonal. And to make them orthonormal, you just rescale them by their magnitude. So you do like W1 over W1 norm. And that will give you orthonormal basis. Some useful property is Gram-Schmidt preserves orthogonal subsets. What does that even mean? It means if you have S and the first few vectors are already orthogonal, so V1 up to Vn are orthogonal, when you apply Gram-Schmidt, what you'll actually find is the new set you get will still have V1 up to Vn, because it turns out the Gram-Schmidt preserves this orthogonal subset. So like if you have S and you notice the first few vectors are orthogonal, you don't need to waste much time finding the first few vectors. They'll literally just be these. Okay, so Gram-Schmidt example, you're given these two vectors in C3. Find the orthonormal basis for them. Okay, so keep in mind we use the standard inner product on C3, which is X bar transpose Y. So I'll just show you an example of that. I don't think I covered it, but 1I0, I26 inner product. This is not the usual dot product. You actually have to conjugate the first vector first. So it's like 1 conjugate. Well, that just looks strange. Okay, I could write it as, okay, 1 conjugate times I plus I conjugate times 2 plus 0 conjugate times 6. But you wouldn't really write this in an exam. Like you just skip to like 1 times I minus I times 2 and then like plus 0. So keep in mind X conjugate transpose Y, which kind of just means you conjugate the first vector and take a normal dot product with the other one. So you have to conjugate the first one. Okay, so Gram-Schmidt, W1 equals V1, that's the easiest one. Then W2 is V2 minus the projection of V2 onto W1, and you'll get this. This is where the minus I comes from, which I just showed you by calculation. And yeah, so when you calculate that, you'll get these two vectors. They ask for an orthonormal one, so you need to normalize it. The norm of 1I0 is the square root of the sum of modulus squares. Square root of 1 squared plus not I squared, but the modulus of I squared, which is still just 1. And like this is root 2. So you get a 1 root 2 here, and you can do something similar for the other one. Okay, orthogonal complement. So the orthogonal complement of a space, I already kind of mentioned complements, but orthogonal complement is a special type of complement. It's where everything in W perp is orthogonal to everything in W. So W, okay, I'll write it like W perp in W perp implies, actually equivalent. W, right? So W perp inner product with W should be 0 for all W in W. Basically, just everything is orthogonal. Like everything in W perp is orthogonal to anything in W. So this is the complementary subspace thing for orthogonal complement. W and W perp, they direct sum to the whole space, which means anything in V can be, any X in V can be written as W plus W perp, where this guy is in W and this guy is in W perp. And also it's a unique representation because the sum is direct. Also keep in mind W intersect W perp is the trivial space because it's a direct sum. So if you have, yeah, so these are just, they're just going to be almost disjoint, I guess, trivial intersection. Now, because there's a unique way to write any X as something in W plus something in W perp, this something in W is called the projection of X onto W, where we're actually projecting onto the space W. It's a bit weird, but what this means is the component of X in the space W. So yeah, and then there's also, you can project onto W perp. So there's this notion of projecting onto a space. We usually mean it as orthogonal projection onto a space. So yeah, it's the component of x which is in W. So first you need to write it as W plus W perp, and then yeah. I think one important thing to note, this thing here. If you want to show something is actually the projection of W onto X, you just need to show X minus that thing is W perp, but what that means is like this. Meaning X minus the projection should be orthogonal to any W. So yeah, so X minus W would be W perp. If you want to show this W is actually the projection onto the space W, you need to show that X minus the projection is orthogonal to anything in W. Okay, so if you have a basis for W and you want something in the orthogonal complement, that something also has to be orthogonal to every basis vector, and it's actually equivalent. So meaning, if X is in W perp, it will be orthogonal to all the basis vectors of W. That makes sense because the basis vectors are in W, and anything in W perp is orthogonal to anything in W. But the other way also works. If X is orthogonal to any BI, then X is actually in W perp. So yeah, let's see the proof. So to prove something's orthogonal to, like in W perp, we need to prove it's orthogonal to any W. Here we have a basis, so you can actually write any arbitrary W in terms of the basis. And then you apply this, you get X in a product sum lambda I x bi. Now, yeah, and then you just get this. This is just wrong. Wait, sorry. This is meant to be lambda I bi. And then you take the sum out. And because X is orthogonal to each of the basis vectors, each of these terms are 0. And you get X in a product W0 for any W, so it's in W perp. Okay, now there is actually a way to write the projection onto a subspace. There is actually a way to find it if you have an orthonormal basis or an orthogonal basis. If you don't have such a basis, there's not a direct formula. But if you do, it's pretty nice. You might have seen this, something similar to this. Remember, I showed if X is in the span of an orthonormal set, then it's like this. But this also works. So the projection of V onto W in an orthonormal case, essentially okay, I'll look at it in this case. You project V onto each basis vector of W and add them up. This only works for orthogonal basis, right? This is also the same here. You take the scalars to be the inner products with Wi, and you just take that linear combination of the Wi vectors. Yeah, okay. So here's an example. We have these two vectors in R4. Find the projection of X equals this thing onto the W, which is span of this. So one way to do this is make this an orthonormal basis. The reason is because I told you projection is easy to find if you have an orthonormal basis. You just project onto each one and add them up. Is this actually orthonormal? I don't think so, because you get 1 minus 1, 0, but then inner product is 1. So one way is to use Gram-Schmidt, which is annoying, but you can do that. Actually, I don't even think we have that here. Okay, but another way is to use the normal equations, or just use equations. What does that even mean? Well, you want X minus the projection. I'll call the projection like W, why not? You want this to be orthogonal to anything in W, right? Remember I mentioned this. This is what you need for W to be like this W to be the projection. So keep in mind W here, the projection onto the space W is actually some combination of these. The projection is actually also part of the space W. So we can write like W equals like A V1 plus B V2 for some A and B. And then you essentially have X minus that thing should be orthogonal to the basis vectors of W. This is what I was talking about. Something's in W perp if and only if it's orthogonal to the basis vectors of W perp. And I'm pretty sure that was for like any basis. You don't even need orthogonal. Yeah, this is for any basis. So what we do is, okay, they used lambda. Okay, we're using lambda and mu. So this is, they're saying Y is the projection, I guess. Okay, so X minus Y should be orthogonal to both of the basis vectors, v1 and v2. Okay, yeah, so essentially what you do is you do that. You take x minus y inner product v1, and you'll get some equation in terms of lambda and mu. I used a and b, but I guess lambda and mu. You can find the equations yourself. It's not too bad. You get this, and you get this. You can try this later at home. Solving simultaneously, you actually find what lambda and mu are, which means you found what the projection is. So this is actually a pretty cool method. Or you can do Gram-Schmidt, but it's kind of annoying. Okay, QR factorization. So, okay, I think I'm doing good for time. So if A is an m by n matrix, okay, QR factorizations, first of all, it's not for all matrices. It's only when the columns are independent. And by the way, that also means n is less than or equal to m. Why am I saying that? Because this is, by the way, a tall, thin matrix is what you call it, like 1, 2, 3, 4, like something like this. Not something like this. Notice that this cannot have independent columns. Why is that? Because like you'd have 3 vectors in R2. They can't be independent, right? Technically, you need to have n less than or equal to m and all the columns independent. So only for those matrices we can have a QR factorization, and it is A equals QR, where Q is the same size as A, so m by n. R is n by n, and you need that so that the total size is n by n, same as A. Now, what are Q and R? Q has orthonormal columns, meaning the columns form an orthonormal set. They're unit length, they're orthogonal. And R is an upper triangular matrix, which is invertible. An example would be like this, 3, 4, 0. This would be an upper triangular matrix, which is invertible. Something like this would not work because 0 is one of the diagonal entries. An upper triangular matrix is invertible as long as none of the diagonals are 0. So R is invertible and upper triangular, and it's also square, by the way. Q is not necessarily square, but the columns are orthonormal. And there's this formula for it in terms of Gram-Schmidt. So what are these? Well, in Gram-Schmidt, you get, imagine the columns of A are A1, A2, up to AQ. Okay, sorry, this is assuming A is P by Q, I'm pretty sure. Not M by N. Then Gram-Schmidt will, assuming they're independent. By the way, Gram-Schmidt only works on an independent set. If it's not independent, Gram-Schmidt will fail. It will give you a 0 vector somewhere. But anyway, we're assuming A has independent columns. This will give you some W1 up to WQ. And then when you orthonormalize it, when you normalize it, you'll get Q1. Okay, this is like bold Q, I guess, up to QQ. So this is the actual orthonormal basis for the columns. So that's what these Qs are. Now this formula is kind of annoying. I would probably put it on the cheat sheet or something. The upper triangular matrix, the diagonals are the norms of the W's. And then for the other ones, you have QI, inner product AJ, where QI is the final vectors you've gotten, and AI are the columns. Okay, so are we getting to the killer question yet? Okay, not yet. Okay, so find a QR factorization of this using Gram-Schmidt. So yeah, by the way, QR factorization you have to do Gram-Schmidt for it. Just keep that in mind. Yeah, so basically you just do Gram-Schmidt to the columns and then you use that. So I already went through Gram-Schmidt, so turns out you get these. And now then you just calculate the norms of W1, W2. And you also need the inner products. So you end up getting this. It's kind of annoying, but yeah. Okay, now we're getting to the killer question. I tried to scaffold this as much as possible, but I still kind of cooked. But we'll go through it. So, I mean, they said there's going to be no calculator, so there might be a bit more proofs in the exam. So I thought we'll just put in some cooked proof question. Okay, so it turns out QR factorizations are unique in a sense. We'll look at the first example. So A has a QR factorization Q1R1. That means, by the way, Q1 is m by n, orthonormal columns. R1 is an invertible upper triangular matrix. Okay, so show that if D is a diagonal matrix with diagonals plus minus 1. So like, what does that mean? 2 by 2 example would just be this. Like, it could be 1, it could be like this, it could be like this, whatever. Okay. Then Q prime R prime is also a QR factorization where Q1, okay, so where Q prime is made by doing like Q1 equals Q prime D and R prime equals D R1. Meaning you apply this diagonal matrix D to R1 and you get a new R. And I guess you can say Q prime equals Q1 D inverse, right? Yeah, because you write multiplied by D inverse. Okay. So basically this is saying if you have a QR factorization already, you can apply this weird transformation to the Q and R and get a new QR factorization, which works. So how do we prove that? To prove it has a QR factorization, you need to prove Q and R, like you need to prove A equals Q prime R prime, right? And you also need to prove Q prime is, you also need to prove Q prime is what? Orthonormal columns. You need to prove R prime is upper triangular. So, okay, let's try this. I forgot what the transformation is. Okay, so Q1 equals Q prime D. And what was it? R1, no, I think R prime equals DR1. Okay, I forgot, what was it? Yes, okay. So first of all, we need to show at least that A is still equal to Q prime R prime. Like if that was not the case, this is not a QR factorization. So what is Q prime? Let's like isolate it. By the way, D is it's going to be invertible. The diagonal entries are plus minus 1. There's no 0 in the diagonals. So we can take the inverse. Q prime equals Q1 D inverse, I think. Yeah, okay. And R prime is DR1. So Q prime R prime should be Q1 D inverse times R prime, so DR1. And you can see that the D's cancel, you get Q1 R1. And this is a QR factorization for A by our assumption, like this is equal to A. That's what they defined it as. So first of all, this does actually still give you A. Now we want to show that it has those properties. Q prime should be orthonormal. The column should be orthonormal. This is actually a cool property, even if it doesn't matter if it's square or not. The columns are orthonormal as long as Q prime transpose Q prime equals the identity. There is some notion of like an orthogonal matrix, which we'll go through later. Those are square. But even if it's not square, it has orthonormal columns if and only if this holds. So we'll just show this. Okay, so Q prime transpose Q prime. So what even is Q prime? Okay, it's this thing, right? So Q prime transpose Q prime should be, I guess, D inverse transpose. Okay, I'll write this. D inverse transpose Q1 transpose. This is from the transpose product rule times Q prime. So Q1 D inverse. Now, Q1 is from the QR factorization of A. So it has orthonormal columns. And therefore, Q1 transpose Q1 is the identity. So this just cancels out. We're left with D inverse transpose D inverse. And notice that it's a diagonal matrix. So it's actually like when you transpose it, it's going to be the same, right? So D transpose inverse, you can say. Wait, is this even right? Yeah, I think so. Okay. So this is just going to be D inverse, D inverse. Now, what is D? It's actually 1 and minus 1s on the diagonal, right? So what's the inverse actually? It's just going to be itself, right? The inverse of this, by the way, the inverse of a diagonal matrix is you just take the inverse, like 1 over each entry in the diagonal, but 1 over minus 1 is still minus 1, and 1 over 1 is still 1. So like, I guess you get this. But anyway, you can see that D squared as well is going to be the identity. This is just a 2 by 2 case, but you do get this to be the identity. D inverse is also D, and you get D squared as the identity. So Q prime transpose Q prime is the identity. That proves it has orthonormal columns. Now R prime, we just want to show that is also going to be, what is it? Upper triangular and invertible. So R prime is D R1. D is, we define D as a matrix, diagonal matrix with diagonals plus minus 1. If you apply this to R1, one pretty cool thing to note is left multiplying by a diagonal matrix. I think it just scales the rows by the diagonals. Yeah. So the rows of R1 are just going to be multiplied by minus 1 or 1, whatever. That's still going to keep it upper triangular. Like, it's not changing anything. It's still going to keep it invertible because the diagonals of R1 will still be non-zero. So this is going to be like upper triangular, and invertible. So R prime is still going to be satisfying the conditions. So therefore, A equals Q prime R prime, and it's still a valid Q of factorization. Like, I think this is a hard question, like, and this is just part A, but like, so I wouldn't think they'd give us something as, okay, I'm not gonna say. Okay, so part A basically says you can take a Q of factorization and apply a transformation to it, you'll get a new one. Now, this is showing part B. If you have Q2 R2, which is another Q of factorization, it turns out that it has to come from this transformation that we did. This is kind of the converse. If Q2 R2 is another Q of factorization, it has to be related to the original one by these two. Okay, so and it also has to be like there exists some D, which works. And here here they're actually mentioning D has to be orthogonal. They're not mentioning it has to be diagonal with plus minus 1 entries. We have like a relaxed condition here. So how do we do this? If Q2 R2 is another Q of factorization, then okay. So first of all, we know A equals Q1 R1, and we also know A equals Q2 R2. What are we trying to show again? Q1 equals Q2D, and okay. So we're trying to show Q1 equals Q2D, and I think R2 equals D R1. Yeah, for some, this time they didn't say diagonal, they just said orthogonal matrix, which means D transpose D is the identity. Wait, was it D R1? Pretty sure. Okay. So let's see, how do we do this? So Q1 R1 equals Q2 R2. We want to show Q1 is Q2 times something, right? Like Q1 times D. We already have that almost. Q1 is Q2 times something. We just like might want to move this to the other side. Keep in mind R1, R2 are both invertible because they're upper triangular and invertible. Q1 equals Q2, R2, R1 inverse, I guess. So ideally, we take a D to be equal to whatever this thing is. What the hell? Do you hear that sound? Do you hear that sound? Okay. Very nice back. It's fast. Okay, I'll go.
Take that back.
Okay. Okay, so D is probably going to be R2, R1 inverse. Now, that also works nicely here, right? R2 has to be D R1. So we're done almost. We just want to show it's orthogonal because they said D has to be orthogonal. So, wait, yeah, was it orthogonal? I think so. Okay. So D transpose D is R2, R1 inverse. Oh, okay, wait. Okay, let's go back to here. Q1 equals Q2D. So this is what we had, and we had the other one, right? Okay, we can try both of them, trying to prove D transpose D is the identity, but you'll see that it actually works better if we try it from this one. So Q1 transpose, I'll just take transpose of both sides. D transpose Q2. Technically it's square, so we can do it the other way as well. But yeah, I think what I'll do, I'll say Q1, Q2, okay. Now, remember Q1 and Q2 are not necessarily invertible, but they are orthogonal. So you can kind of invert them in some way if you multiply by the transpose on the left. It's kind of like a left inverse. So Q2 transpose Q1 equals Q2 transpose Q2D. But this is the identity. This is what, when you have a QR factorization, you'll always have this property for the Q. So D is also actually equal to this. Is this orthogonal now? D transpose D is Q1 transpose Q2 times D. And you get this. Okay, so let's see. So Q is actually right. It should be. Q2 transpose Q1. Yeah. Okay, now I'm pretty sure. Okay, wait. So does this actually work? Q1 transpose. This isn't necessarily the identity, right? Okay, maybe I'm tripping. Let's go back and see what's happening. What happens if we do it from this direction? So D transpose D is, let's see. Wait, is the question? I remember the question. Okay. I'm pretty sure this is actually meant to be switched around. I'm not copying, like I'm pretty sure this is meant to be switched around. This is meant to say, okay, I'll fix this when we upload the slides. I'm pretty sure this is actually meant to say this one's upper triangular and this one's orthogonal. Okay, but I'll fix the slides if that's the case. Yeah, okay. Now let's move on to part C. Part C is an induction proof. Prove that DEI equals plus minus EI for all I in this using strong induction. So this is actually proving that D has to be this diagonal matrix with plus minus ones on the entries. Okay, what I'll do is I'll almost leave this up to you, but I'll just go through an example and that will probably give you some intuition for the proof. So we're assuming that this matrix D is orthogonal and upper triangular. It turns out if you have such a matrix, it will always have that property. Let's just look at an example, right? 3 by 3, for example. If it's upper triangular, it has to be like this. Let's write it like this: A, B, C, D, E, F. This is what it means to be upper triangular for a 3 by 3, for example. If it's also orthogonal, the columns are orthogonal and they're also unit length. An orthogonal matrix means the columns are orthonormal. It's a bit annoying, orthogonal and orthonormal. They should have called it an orthonormal matrix. That's just how it's defined. So if A00, the column is orthonormal, it has unit length. So I mean, you can say A equals 1, or actually A equals plus minus 1, right? So this has to be plus minus 1. And that already proves it for the first column. By the way, this was, if you go back to the question, it's proving this is true for all columns. So that already proves that D E1 equals plus minus E1. Now, for the second column, we use the fact that the columns should be orthogonal. If you take the inner product with this, we're assuming real matrices. This is just going to be B. Oh yeah, okay. So B, just B, right? And then plus 0 and 0 should be 0. So B has to be 0 as well. And now you use the fact that, this is D, by the way, use the fact that the columns are unit length. This D also has to be plus minus 1. And now for the final column, you'd use the orthogonal thing again. You take the inner product with this one and this one. And you'll notice that you just get C equals 0. Yeah, because all the other ones cancel out. And now you'll take the inner product with the second one, I guess. So this one and this one. And you'll get E equals 0. So then this thing. And again, you use unit length, so F should be 1. Oh, sorry, plus minus 1. And here you have a diagonal matrix where the diagonals are plus minus 1. So that's kind of the idea about the strong induction. If you want to formalize it, you can try it later. But like this is taking a bit of time. Okay, in terms of N, how many distinct QR factorizations does A have? So what we proved in part, let's see, what have we proven? We've proven if you have a QR factorization, you can make a new one by applying a matrix D where the diagonal entries are plus minus 1. So how many such diagonal matrices are there? If the diagonals are plus minus 1 and there's n diagonals, well, for each of them, you can have 1 or minus 1. That's like 2 choices. So there's going to be 2 to the n. 2 to the n possible, 2 to the n possible Ds, that matrices D, which we have used. So for example, if it was 2 by 2, you could have this, you could have this, you could have this, etc. And the last one would be like this, 2 to the 2, 4. You have 2 choices for each diagonal entry. So there's 2 to the n possible matrices D that we used in part A. This means if you have a QR factorization, Q1R1, there's 2 to the n possible ones you can generate from that. Then part B shows if you have any other QR factorization, then it actually has to come from this some matrix D of that form. And that means it has to come from one of the 2 to the n generated ones. So actually, this means that there has to be exactly 2 to the n different QR factorizations. Okay. Okay, so where's the induction proof? Okay, wait, let me go back to this one. Let's see. Okay, so for part B, what we had was Q1 equals Q2D. So let's see, so D, I think D transpose might work easier. Let's try that. D transpose Q2 transpose Q1 times Q1 transpose. Okay, wait, where is this going on? Let's see. D transpose Q2 transpose Q2, D equals I. Okay. So we use the fact Q1 is equal to DQ2. And because Q1 transpose Q1 is I, we get Q1 transpose Q1 equals, okay, yeah. Yeah, I think this actually has to be fixed. There was an issue there. I guess this is what happens when you put a killer question. So let's move on to adjoints. So the adjoint is a linear map which allows you to switch the order of an inner product with W and T of V. It's a bit weird. So if you have W and T of V and you take the inner product, then you can switch the order. You can move T to the other side as long as you take it the adjoint. It's some other linear map. And what's strange is the inner product switches from that of W to that of V. So yeah, so the inner product on the left side is W, the inner product on the right side is V. Now, some properties of adjoints is they're conjugate linear. So in the sense that S plus T adjoint is S adjoint plus T adjoint. But if you scale T, if you consider the map alpha T, you'll get an alpha bar here. Okay, so different inner products yield different adjoints. So notice how we're defining this with respect to two specific inner products on V and W. But if you use different inner products, the adjoint map will actually be different. And you can write the adjoint of a linear map in terms of matrices. It's the conjugate transpose, but this only works if you use orthonormal bases, B and C. So this means that if you have T, B, C, and you take the star of this, which is the conjugate transpose, you will get the matrix for T star with respect to the same bases. You just switch the order because T star goes from W to V. This only works when B and C are orthonormal. Don't think that it works for any sort of bases. And we'll actually show something like that. But how do you compute the adjoint of a linear map in general? So not for a matrix, but actual linear map. So usually you find a formula for T star of W. So notice this is how we define the adjoint. And you need to find what T star of W is. So what you do is you compute W and T of V, and essentially then you also compute, then you need to write it in the form something in a product V. So notice that this something is just going to be whatever T star of W is. Okay, yo, is anyone here? Yo, okay, that's crazy. Okay, so write this in the form something of VW. Whatever that something you get will be T star of W. And it'll be in terms of W. And that means you have a formula for T star. T star is a linear map, so you just need it evaluated at an arbitrary input to kind of determine what it is. Okay, so here's an example question. So you have this inner product. You don't need to prove it is an inner product. And you have this linear map. Find a formula for T star. Okay, so all you do is use the fact, what is it? X, okay, I guess W in a product T of V. You need to do something like that. So how are we going to define it? Okay, so what is W? W here is an element of Y. Y is a polynomial. Okay, so we could say P0 plus P1T in a product T of X. First of all, we're going to find what this is based on the inner product they're giving us. So based on the inner product they're giving us, it's not too hard to figure this out. You'll get this. Now, the goal is to write this in the form something in a product X, but that something is going to be T star of P0 plus P1T. And also you have to make sure you use the inner product of the codomain, right? No, if it's W T of V, okay, I actually have to use it of the domain, right? Because this will be T star W and V. Yeah, you have to use it of the domain V. So in this case, it would be capital X, which is R2. So we use it, we use the standard inner product on R2, which is just a dot product. So we need to write this thing in the form of a dot product with X. So a dot product with X will just be in terms of X1 and X2, right? So if you do that, do some rearranging, you'll get X1 times this plus X2 times this. This is an inner product with X, the vector X, right? It's the inner product of Y and X, where Y is just whatever this thing is. And this is going to be what T star is, T star of P0 plus P1T. Now, if you repeat the same question with a different inner product, for example, this one here, you actually find that we get, what do we get? Oh yeah, you find that we get something else. I won't go through the details, but you get this here, 8P0 plus 13P1. Sorry, that's, my handwriting is terrible. So 8P0 plus 13P1 as the first entry. Second entry doesn't matter because what I'm saying is this is going to be different from the one we found before, which shows that the adjoint is different based on what inner products you define. Okay, so some important maps. A unitary map is one where T star equals T inverse. A self-adjoint map is one where it's equal to its adjoint. Now, isometry is one which preserves norms, preserves magnitudes. It turns out isometry is the same as unitary. Here are some properties of unitary maps. So T is unitary if and only if T star equals T star, T equals I. Then you have a bunch of these. So preserves inner products, preserves norms, unitary if and only if the columns are orthonormal. If it's a real matrix, you would say it's orthogonal matrix. Unfortunately, it's not orthonormal, but yeah. Okay, so unitary maps are invertible, so are also injective and surjective. Yeah, they're invertible because the inverse is actually the adjoint. Okay, so we have an inner product here, and let T be given by this. We want to show the matrix is self-adjoint with respect to it. So now you can just see for yourself, T of 1 is going to be 0. Like it just doesn't care about the constant component. T of T is also, oh, okay. T of T is actually B, I'm sorry, it's like 1. Because if you take B equal to 1, A and C to 0, you'll get 1. But T of T squared equals 0. Using the standard basis, you can write it as like what? 0, 0, 0, 0, 1, 0, and 0, 0, 0. Now this matrix is clearly self-adjoint, like it's equal to its conjugate transpose. It's a diagonal matrix, and it's just like the entries are real, so it's equal to its conjugate transpose. Okay, now show that T is not self-adjoint. So interestingly, T has a matrix which is self-adjoint, but T itself is not self-adjoint. To prove that, okay, what would it mean for it to be self-adjoint? It would mean like T of W, T of V equals T star W V, but for it to be self-adjoint, T star it should just be T. This would be true for all W, V, whatever, if it's self-adjoint. We just need an example where this does not hold. So we need an example where W, T of V inner product is not equal to this. First of all, what was the inner product of polynomials that we defined? We defined it as the integral 0 to 1 of the product. Okay, so let's see. So W, what even are the spaces again? I completely forgot. It's from T from P to R. T. Okay, so yeah, we can check this for ourselves. So one pretty cool thing you could do is take one of the vectors to be 0. So take like W to be 0, for example. Then this is, by the way, when I say vector, I mean polynomial, because then you know the left-hand side should be 0. We want to check if the right-hand side is not 0. So we can take, okay, well, we just need the inner product to be 0 technically. So if you do T of P inner product Q using this, it would be 0 if we take it, T of P would be 0 if we take something like what? Like 1, T of 1 equals 0, right? So we can try like P equals 1, and then Q could be something else like T, and then these are just standard choices, and you get this for the integral, which is half, but T of P was 0. So the inner product of T and P and Q should be 0, but when you take the star, or sorry, when you reverse it with this, you actually don't get 0, you get half, which means it can't be self-adjoint. Okay, so suppose we have a normal map and it's also idempotent, which just means T squared equals T. First of all, okay, I'll leave this as exercise. If it's idempotent, you can actually show this holds. We did this in the assignment actually. Second one, show that kernel of T equals kernel of T star. Okay, so let's see. So Tx equals 0 if and only if T star x equals 0. This is assuming normal. Yeah, so normal map I think has this property. I think you do it with inner products surely. So if Tx equals 0, then I guess Tx y equals x T star y. Let's see. Yeah, so this is 0. And so what we have is T star y inner product this equals 0, and this holds for all x. So, okay, wait. Let's see. I have to use the fact is normal. Okay. So we have to use the fact that T star equals T star T. So if Tx equals 0, oh, okay, I forgot the condition, the norm thing. So norm of Tx equals norm of T star x. I should have mentioned this. This is one of the nice properties of normal maps. Okay, I think I'll just prove this because this basically just is the whole thing. So Tx inner product Tx equals T star Tx x. And because you can switch the order, because we're assuming it's normal, you get this. And then now you move, how should I write this? You move the T to the other side by taking the adjoint. So this proves that norm of Tx, squared equals the norm of t star x squared. So tx is 0 if and only if t star x is 0. So that shows this. Okay, so now show that t equals t star. To prove two linear maps are the same, you can show that they agree on, like, they have the same outputs for a given input, like tx equals t star x. So surely I have space. Okay, I don't have space. So tx equals t star x for all x. How do we do that? So we've shown it's idempotent. We've shown the kernel of t is the kernel of t star. So maybe we can show that t. How should we do this? Well, we know t is idempotent, right? Maybe what we can do is, like, we want to show tx equals t star x. Okay. So we can take t of both sides, t squared x, because we want to use this fact, right? Equals t star, sorry, t star x. But t star is the same as t. Wait, I'm saying, sorry, t squared is the same as t. So this should actually give tx equals t star x. But I'm going to reverse the order because it's normal map, right? Now, yeah, so this is tx. Now t star x equals tx. What would be t star x now? So we can multiply by t star, I guess. T star squared x equals t star tx. Notice how technically you can take star of both sides. So t star squared is also just t star. So t star x is this thing, and it's also equal to this thing. So t star x equals tx. It's kind of a bit trippy. Okay, so let's just go through this again. Yeah, so be sure this works. Okay. So if T is a unitary map, then T of W perp equals T of W perp. So let's see. So by the way, what this means is this is like taking a function of a set. Okay, how much time do we have? Are we even on eigenvalues? Okay, we're not even on eigenvalues. Wait, are we? I don't even remember. No, we're not. Okay, you just kind of speed this up. Okay, I think this one isn't actually too bad. So I think, which one was the more difficult direction? I think I'll just do that one. Okay, so we'll suppose, okay, T of W perp. So I'm just going to show T of W perp is a subspace or subset of T of W perp. So suppose you have X is in T of, suppose you have X is in T of W perp. What does that mean? That means X is orthogonal to anything of the form T of W. So X T of W equals 0 for all, I guess you can say for all W. Right? Now we want to show we want to show X is in this thing, meaning X is of the form T of, why not? Let's just say U, where U is in W perp. First of all, can we even write X as T of something? Well, because T is unitary, it is invertible, so we can write X as T of something. It's surjective, right? So we can write X as, I guess, T of U. We just need to explain why U has to be in W perp. Well, this is going to give T of U, T of W. And then one useful property I mentioned was unitary maps preserve inner products. So U, W should be 0 because, because these are actually the same. They preserve inner products. So the inner product of T of U, T of W is the same as the inner product of U and W because we're assuming this is a unitary map. And this proves U is orthogonal to any W in W. So U has to be in W perp, meaning X is of the form given here. And I'll leave the other direction as exercise. Okay, so I will skip this first one because it's actually in a tutorial. But yeah, so we'll just move on to part B. Show that rank T equals rank of T star. So the rank is adjoint invariant. So rank is dimension of the image, right? So you want to try to take dimensions of stuff in part A. Just taking dimensions like immediately gives nullity T star equals the dimension of the orthogonal complement of this. So notice that mt O plus mt perp is what? It's not going to be V because mt is in W. So it's going to be W. So the dimension of the orthogonal complement is actually the dimension of W minus the dimension of the image of T. dmW minus rank T. Okay. So now rearranging, you get rank T dmW minus nullity T star. We just want to show this is rank of T star. So T star actually goes from W to V. W to V. So by the rank nullity theorem, this is like just straight up rank of T star. Show that T is injective if and only if T star is surjective. Okay, so T injective means that the nullity is 0, right? The kernel's trivial. So, or you can say the rank, full rank. So rank of T equals, oh, sorry, that's wrong. So injective if and only if the nullity is trivial, right? So it's nullity is 0. So let's see. So nullity T, well, isn't that dmW? Sorry, dimension of V minus the rank of T. And this is 0. Okay, so it's 0 if and only if rank T equals dim V. So 0 if and only if rank T equals dim V. This is the same as rank of T star equals dim V. The reason is because rank of T is rank of T star. Now, T star is from W to V. The rank of T star equaling dimension of V means that T star is surjective, right? It means the image of T star has to be V. So that basically proves it. Okay. Okay, least squares. So least squares is when you're solving ax equals b, but there's not a there's not a solution. So you find the closest solution, which minimizes norm of ax minus b. And essentially, it's just this: a star ax equals a star b. You want to solve this system. If a star is invertible, then you can take the inverse and just do it like that. But in general, you're going to have to solve a linear system. So what on earth is this? Find the least squares best fit of this solution. It's essentially trying to find a line which, well, okay, in this case, they've written it like this. It's technically just solving a star m star mx equals m star y. So we just solve it like, you just find what m star m is, and then seems to be this. Oh, sorry, no, this is m, and then m star m will be whatever this is on the right. And we just put this together and you'll get this as well as computation. Projection matrices, this is mainly to find the projection onto a space. Like, you know what, I should mention though, that if you're trying to find the line of best fit through points, usually you end up with ones on the first column. I don't know why this one doesn't have that, but if you're trying to find the line of best fit through points like 1, 2, 3, 4, and 5, 6, for example, usually you have like y equals like ax plus b as a line. Usually say like ax plus c, you need to satisfy, like your solution would, the equations would satisfy each of these, right? So you need like 2 equal to c plus a, 4 equal to c plus 3a, 6 equal to c plus 5a. And for this, you essentially get, what do you get? 1, 1, 1, 1, 3, 5, and 2, 4, 6. This doesn't have a solution, but actually, yeah. So then what you do is, this is your matrix A, and this is your vector B, and the vector X is actually CA. Usually you do it this way. Unfortunately, C will come first in the vector, and you solve A star AX equals A star B. Okay, so, oh yeah, you can revisit this example by finding the projection matrix. It turns out if you want to project onto space, the orthogonal projection is given by this, A star A inverse A star, and you apply that to B, and that will give you the projection onto the space. So here, the matrix A is made by just taking the vectors v1, v2. You find A star A inverse A star, sorry, A star A inverse A star. It's a lot of computation, but you just do it one by one, and you get this. Okay, determinants. So determinant, a permutation is a reordering of, okay, it's a permutation, right? It's like we take elements, n distinct items, and you reorder them in some way. You can think of it kind of as a function, like you map, imagine you permute the set 1 to n, then 1 will map to something, it could map to 5, n, 3, whatever. We'll call that p1, and etc. So 2 will map to something, etc. Now you can define a permutation as like a function, like sigma of 1 equals 2, sigma of 2 equals 1. Imagine you just had 1, 2, 1, 2 as your set. And I guess that's not a set, that's an ordered pair. So you could just define it like, imagine you had this, you had n equals 2. A permutation would be something like this. Sigma goes from, sigma of 1 is 2, and sigma of 2 is 1. Okay, so when you permute two elements or swap them, you call this an inversion. So there's also a sign of a permutation, which is just kind of the number of inversions. So for example, for this, you can see it starts off 1, 2, 3, 4, 5. If you swap 2 and 3, then this is one inversion. Sign should be -1. So sign is technically -1 to the k of the number of inversions. Then you can define the determinant like this. I'm not sure how likely this is going to come up, but yeah. This is the cofactor expansion. This is the one we use more often. Here are some nice properties of determinants. So upper triangular or lower triangular matrix, the determinant is just the product of the diagonals. Determinant is transpose invariant. Determinant of A star is the conjugate of the determinant of A. And if you apply a permutation to the rows or the columns of A, the determinant is multiplied by the sign of the permutation. Usual case of that is like if you switch two rows, then determinant negates. Switch two columns, the determinant negates, etc. Yeah, so the row replacement or the main row operation you use in Gaussian elimination, for example, that doesn't change the determinant. And if you multiply a row by alpha, then the determinant scales by alpha. Similarly for columns. Okay, so here's an example. We have this matrix here, and explain why the determinant is this. So the idea is to try to use some sort of row operations because those preserve the determinant. We could also do column operations, but we'll see what happens. Well, if we do row operations like adding these two rows, what do you get for the first one? You'll get like A plus B minus C here. Let's see, B minus C plus A, okay, which is the same. And then 2A plus B. And then, okay, do I have this? Yeah, so, okay, where is it? Okay, yeah, and then if you do it again, but with this one, So add these two rows. Let's see. I think what we'll do is we'll actually, since there's going to be ones here, we might replace the first row, R1, with, let's see, R1 maps to like R1 plus R2. So then on the first one, we get A plus B minus C. And then here we get what? A plus B minus C and 2A plus 2B. And then if you add, if you do that again, but now we do 1 maps to 1 plus R3, then you'll see that we do get A plus B plus C, A plus B plus C, and then, yeah, A plus B plus C. Okay. So then you can take the A plus B plus C out, and you get this essentially. Notice how these last two rows haven't changed, which is why we don't want to do the row operation to change those two rows. Yeah, so essentially just doing this. Okay, now explain why the determinant of B is this thing. So they seem to have changed a few things to the matrix. The first row has changed a bit. Second row has also changed. Okay, all the columns, first column is the same. Second column has changed, third column has changed. So maybe we might think to do column operations. So in fact, if you add these two columns, yeah, if you add, oh, sorry, let's go back here. If you subtract these two columns, so let's say C1 for, okay, C for column, C2 maps to C2 minus C1. What are we going to get? B minus C minus A minus 2B. So we get minus A plus B plus C. And I guess that's what they have here. And for this one, you can see we'll get 2B minus 2B, which will be 0. And yeah, it's essentially just doing that again. C3 maps to C3 minus C1. We'll get this. Now notice this is a lower triangular matrix. The determinant is just the product of the diagonals. So when it asks us here to find the determinant of B, we just do that. We take the product of the diagonals, and this is what we get. So determinant of A would be A plus B plus C times that, because that's what we had from before. Okay, eigenvalues, eigenvectors, last topic. So eigenvalues, eigenvectors are only for linear maps from V to V. They have to be from the same space. Domain and codomain have to be the same. The reason is it's basically T of V equals lambda V. V is an eigenvector, lambda is an eigenvalue if this holds, and V has to be non-zero. A useful characterization is this thing here. Lambda is an eigenvalue if and only if T minus lambda I is not invertible. The reason is because T minus lambda I, V equals 0 if you rearrange this, and V is assumed to be non-zero, meaning you have a non-trivial kernel, so it's not invertible, not injective. Because the dimension of this domain and codomain are the same, that's equivalent. So yeah, this is actually a pretty useful characterization of eigenvalues. A space is T invariant, means that it's closed under T. So if you apply T to anything in the space, you'll just get another vector in the space. So T of U is a subset of U. Properties of eigenvectors. Eigenspaces are T invariant. I think, yeah, this one's here. Eigenvectors from different eigenvalues are linearly independent. So that means, okay, so if you have lambda is not equal to mu, then any eigenvector, lambda eigenvector, will be independent from any mu eigenvector. Okay, so yeah, also eigenspaces have distinct eigenspaces have trivial intersection. Okay, so there's something called the characteristic polynomial, which is solved by determinant of Ti minus A. This ensures that it's always monic. And if it's a matrix, an n by n matrix, it will be a degree n polynomial. Okay, so multiplicities. There's some notion of an algebraic multiplicity and a geometric multiplicity. The algebraic multiplicity is the multiplicity of the eigenvalue in the characteristic polynomial. So if you had like t minus 1 squared, t plus 5 or something, 1, t equals 1, that would be a eigenvalue with multiplicity 2, algebraic multiplicity 2. Minus 5 would be multiplicity 1. Geometric multiplicity is the dimension of the eigenspace. Have I defined eigenspace? Well, E lambda, or the eigenspace, is the kernel of A minus lambda I, or lambda I. This should technically be lambda here, same as the kernel of lambda I minus A. But yeah, so this is actually just a set of all eigenvectors, also including 0, because a kernel is a subspace, it will contain 0. The dimension of that space is the geometric multiplicity. You have this nice AMGM inequality, which is not related to the actual AMGM inequality. The algebraic multiplicity is greater than or equal to the geometric multiplicity. And this always holds. Trace and determinant. So the trace is the sum of the eigenvalues, and the determinant is the product of the eigenvalues. This is a pretty useful fact. The trace is also the sum of the diagonal elements, but it also has this characterization. So if you already know one or more eigenvalue, you can use the trace and determinant to kind of figure out the rest. Okay, so characteristic polynomial of a 2 by 2 matrix, it's actually always of this form. But if you're finding eigenvalues of a 2 by 2 matrix, it's usually better to just find the trace, find the determinant, and inspect the two solutions. So you just need to inspect two numbers which add up to the trace, two numbers which multiply to the determinant. So you don't really need to always write out the polynomial. Okay, so so we have this pretty cool way to find find the kernel, find the eigenvector if the geometric multiplicity is 1. So you're finding elements of the kernel of A minus lambda I, and you know that it's the dimension is 1. So this kernel is spanned by just one vector. This works for 3 by 3 matrices, which is when real matrices. And how does this work? Well, let's write A minus lambda I with rows R1, R2, R3. Keep in mind this is for A minus lambda I. Anything in the kernel, so if you want A minus lambda I v equals 0, then one thing you should know about matrices is the entries of A minus lambda I v is just going to be the dot product of v with the rows. You can see how that works when you actually do a computation. You want this to be the zero vector, which means R1 dot v should be 0, same for R2 and R3. So to find a vector in the kernel of A minus lambda I, all you need to do is find a vector which is orthogonal to the rows. Now, if if the nullity or the kernel of this has dimension 1, then the rank would be dimension 2. So 2 of the rows are independent, and we can take the cross product of those 2 rows. And essentially that will give you a vector orthogonal to both of those rows, right? And such a vector, therefore, will actually be an element of the kernel. So essentially you don't need to do row reduction to find an element of kernel A minus lambda I, assuming that the geometric multiplicity is 1. So an example is if you have this matrix here, you want to find E minus 1. First of all, consider Q plus I, which is the same as if you just consider this matrix as A, the kernel is the same as the kernel of A plus 11I. And to find the kernel of this matrix, you could row reduce, but it's kind of annoying. Instead, you can just do one computation, which is take the cross product of 2 rows. So here I chose this last row and the first row. Fortunately, the numbers are still kind of annoying, but it might be better than just having to do row reduction, because you only have to do a few multiplications here. Then you can scale this to get this here. So this vector is orthogonal to the rows, so it will be in the kernel, and yeah, that would be the eigenvector. Okay, so here's a practice question. I think I'll skip this one, but I'll just explain what it is. Basically, if you have an annihilating polynomial of A, which just means a polynomial such that Q of A is 0. For example, imagine A squared plus I equals 0, or A squared minus A equals 0, or whatever. then any eigenvalue of a is a root of this annihilating polynomial. So if a squared minus a equals 0, notice the polynomial is like t squared minus t. Any eigenvalue has to be roots of this. So what? T minus 1. Any eigenvalue has to be either 0 or 1. And for part A, what it's saying is if lambda is an eigenvalue of A, Q of lambda is an eigenvalue of Q of A. So if, a simple example, if lambda is an eigenvalue of A, lambda squared is an eigenvalue of A squared. But yeah, the proof would just be to write P polynomial, sorry, the polynomial Q as an arbitrary polynomial, like sum of AKT to the K, and you can have a go at that. Diagonalization, so a square matrix is diagonalizable if and only if it's similar to some diagonal matrix, and that just means A equals PDP inverse for some invertible P. A linear map is diagonalizable if and only if the matrix is diagonal with respect to some basis. So keep in mind that's kind of like how you're saying it's similar to a diagonal matrix, because the transformation matrices of a linear map are all similar. As long as you can find one transformation matrix which is diagonal, you're good. By the way, the bases have to be the same for both codomain and domain. Okay, so what's pretty interesting is if you have a diagonalizable matrix, all the roots, all the eigenvalues are in the field. Meaning if you have a real matrix which is diagonalizable over R, then all the eigenvalues are actually real, or all the roots of the characteristic polynomial are real. The reason is if it's diagonalizable, it's similar to some diagonal matrix D, and obviously D is going to be in N of F, meaning the diagonal entries are in F. Now, the characteristic polynomial is a similarity invariant, so the characteristic polynomial of A is the same as that of D. A diagonal matrix is a very simple polynomial, characteristic polynomial. It's just going to be this, where the diagonal entries are these lambdas. These lambdas are all in F because we're assuming D is a like imagine F was R. We're assuming D is a real matrix, so the diagonals should be real. Therefore, these things which are going to be the eigenvalues of A are real. Now, if F was C, this is kind of obvious, like because all the characteristic polynomials, all the roots of the characteristic polynomial of A should be in C anyway. This is more special if F is the like R. Yeah, so if you want to show a real matrix is not diagonalizable over R, you can just show it has like a non-real eigenvalue, like I, for example. Okay, so turns out that a matrix or linear map is diagonalizable if and only if there's a basis of eigenvectors for V. Or you can say there's n linearly independent eigenvectors, or you can say the geometric multiplicities sum to n. Number 3 is usually the more common one you use. The AM equals GM for each lambda. Algebraic multiplicity equals the geometric multiplicity. How do you diagonalize a matrix? You find the eigenvalues, find the algebraic multiplicities, then find the geometric multiplicities by solving A minus lambda I with 0. That's finding the kernel. If the dimensions don't match, then it's not diagonalizable. But if they do match, you can continue. Then to do A equals P D P inverse, you take D with diagonals being the eigenvalues according to multiplicity, and you take P to be the eigenvectors, so the basis vectors of each eigenspace, where Vi belongs to the eigenspace of lambda I. Okay, so let's just look at this quick example. So here we have, for a 2 by 2 matrix, we have the trace is 5. The determinant is 4 minus 2, which is 6. So what? By inspection, I guess 3 and 2 are the eigenvalues because they add up to the trace. They multiply to the determinant. So then now you know the eigenvalues. In fact, it's going to be diagonalizable because you have 2 distinct eigenvalues. If you have n distinct eigenvalues in general, it will be diagonalizable. It's not equivalent though. It's possible to be diagonalizable. but not have n distinct eigenvalues. So anyway, so if this is a minus 3i, surely I have it somewhere. Okay. We're not finding it? Okay. Okay, so, I mean, you can do it yourself, a minus 3i. You just subtract 3 from the diagonals. So 1 minus 3 is minus 2, 1 minus 1, 2. And the kernel of this is going to be 1, 1. Like, you can kind of inspect it. You can see that if you pull 1, 1, you'll see that you'll get 0. So this would be the V2 for eigenvalue 3. And similarly, you'll solve a minus 2i, 0, this linear system, you'll get 2, 1. And so the matrix P, you can take it to be 2, 1, 1, 1. And D is going to be, well, 2, 1. The first column is with respect to the eigenvalue 2. So you need to make sure you put the corresponding eigenvalue here. Second column is for 3, so it'll be this. And then A equals PDP inverse. Then for this one, you can find the eigenvalues. And yeah, so then you'll get this. This one, the algebraic multiplicity geometric multiplicity will be 1. Pretty important result is if the algebraic multiplicity is 1, geometric multiplicity also has to be 1. The reason is because we have this here. So, and we also have geometric multiplicity can't actually be 0 because we assume it's an eigenvalue. The dimension of the kernel of a minus lambda I cannot be 0 because if it was 0, lambda would not be an eigenvalue. We're assuming that a minus lambda I does not have a trivial kernel, meaning we're assuming there is actually a non-zero eigenvector. So we have this. Okay, I didn't circle that properly. So if AM equals 1, then GM has to be 1 as well. All we really need to check is the geometric multiplicity of the eigenvalue 2, is that equal to 2? So you take the kernel of a minus 2i, and you do actually get 2 vectors, so this does work, and you get this, so yeah. Okay, so we won't go through this example, but this is just asking, is this linear map T diagonalizable? You just need to show, what does it mean? You need to show that it has a basis such that the matrix is diagonal with respect to that basis. Well, if you just use this basis here, you'll get this. This is not diagonal, right? But what you can actually just do is show that this matrix is diagonalizable, because then it would be similar to some, if I call this matrix A, it would be similar to some D, and then that means that T would have some basis where the transformation matrix is D. So all you need to show is this transformation matrix is diagonalizable, which you can do with the usual methods. Okay, spectral theorem. So, okay, we already talked about normal operators, but I think we're going into more detail now. The normal operator is one which commutes with its adjoint, meaning T star equals T star T, or A star equals A star A. Okay, so here were some of the results I was going to say. The norm of T of X is the norm of T star of X. This is for normal maps. If T is normal, then any T minus alpha I is also normal. The eigenspace of T with eigenvalue lambda. Okay, what that means is if TV equals lambda V, T star V equals lambda bar V, conjugate essentially. And if T is normal, distinct eigenspaces are orthogonal. Meaning, if you have two eigenvectors from distinct eigenvalues, then they'll be orthogonal. Here's the spectral theorem for normal maps. Basically, a matrix is normal if and only if it's unitarily diagonalizable, which means you can write it as, I guess, U du inverse, where U is unitary, which means U inverse is U star. So you can say U du star. This is actually equivalent. If you have a normal matrix over C, then that's equivalent to saying it's unitarily diagonalizable. There's also a spectral theorem for over R for self-adjoint matrices, or I guess you can say a real symmetric matrix, because that's essentially the same thing, for symmetric matrices. First of all the eigenvalues are real, and eigenvalues, distinct eigenspaces are orthogonal, and it's unitarily diagonalizable. But technically, if we're working with R, we could say it's orthogonally diagonalizable. Q, D, Q transpose, you can say. So then there's also some corollaries. If A is unitary, then what does that mean? It means U star, I guess, is the identity. But that also means U star, U is the identity. Notice how U and U star commute, they're equal. So any unitary matrix is also normal. So then you can apply the result for spectral theorem for normal maps, and you get that such a unitary matrix is also unitarily diagonalizable. So this is actually just a special case of the one for normal maps. But this is pretty useful. Any unitary matrix has eigenvalues units length or unit modulus. That's why they're called unitary. So just a summary here. So normal on C is equivalent to unitarily diagonalizable. Real symmetric is equivalent to orthogonally diagonalizable, which is orthogonally unitary is similar thing. And from these, you have kind of corollaries. Self-adjoint on C is the same as unitarily diagonalizable. Oh, sorry, it implies it, because if it's self-adjoint, T equals T star. That also means that obviously T star equals T star T, meaning it's normal. And then you just use the one for normal maps. Similarly for unitary. So here's an example. We'll assume P is orthogonal. So that means it is, you can say it's unitary over C, right? Even though you think, wait a minute, there's no complex entries here, but you can extend it to C. Like any real number is still complex. So P is technically still unitary. If it's orthogonal in the real case, it's also unitary over C. So all the eigenvalues are unit length, and it's unitarily diagonalizable. So okay, this is just like Gaussian elimination, right? So we will conveniently skip that one. But then for part 2, explain why the spectrum of P is this. Spectrum, by the way, is just the set of all eigenvalues or multi-set of all eigenvalues. So why is this the case? Okay, so they've shown that kernel of P minus I is what is this? This shows that what 1 is an eigenvalue, right? Okay, so 1 is an eigenvalue. What else? And it also has geometric multiplicity 2. Notice how the kernel of P minus I has dimension 2. So the algebraic multiplicity cannot be less than it. It has to at least be 2. So we must have 1, 1, and then 2 other eigenvalues. Because I guess we can use like the trace. Okay, trace doesn't seem to help. Okay, so because they're all going to be unit length, the other ones are just going to be like I minus I or minus 1, minus 1. But, okay. Yeah, so because they're all unit length, we know that it's 1, 1, and then I minus I. Because trace, I think, what was the trace you get? Unfortunately, there's a 1 on 9, so it's kind of annoying, but trace would be 1 on 9, 10 plus 8, so 18, so 2. So if we had 1, 1, then there is 2, right? So 2 plus the other eigenvalues, I can call lambda and mu, is 2, so lambda plus mu equals 0. Now, because eigenvalues, if the other ones were still real, like if we had one of these were minus 1, then this wouldn't work, right? Like we also need to make sure eigenvalues come in conjugate pairs because this is a real matrix. So because they're unitary, the unit length, the eigenvalues, unit modulus, they have to be I minus I. They can't be anything else. Okay, so I think, okay, so show that a normal matrix with all eigenvalues real is self-adjoint. We need to use the spectral theorem. What does it mean for it to be normal? It's equivalent to unitarily diagonalizable. So A equals UD U star. It's saying all eigenvalues are real. So, by the way, the matrix D contains the eigenvalues as the diagonal entries. We're assuming they're all to be real. So D is a real matrix. Self-adjoint, we just need to show it's equal to its adjoint. Using the properties of adjoint, you get U, D star, U star. But D transpose is itself, because D is a diagonal matrix, they're symmetric. D conjugate is still D because it's real. So D star is still just equal to D, and this is A. So A star equals A, meaning A is self-adjoint. Okay, so then here's some other practice questions. So I'll just read them out. And if A is, okay, basically this says A, B, and BA have the same non-zero eigenvalues. This doesn't even need A and B to be square. You just need AB and BA to be square. Next one is find the relationship between the eigenvectors of T and STS inverse. If you want to do it in terms of matrices, you can like A and BAB inverse or PAB inverse or something. Next one, show that lambda is an eigenvalue of A if and only if lambda bar is an eigenvalue of A star. You might need to use determinants for this, I'm just saying. Next one, suppose you have a 3 by 3 matrix with these eigenvalues. Show that there's an x such that this holds. Then 5, any polynomial of t is normal, assuming t is normal. And 6, any one-dimensional t invariant subspace is a subspace of an eigenspace. Okay, before we finish, I'll just mention this. I think there was a mistake in the killer question, so hopefully we'll fix that up before we upload the slides. Okay, let me go all the way up. Yeah, so the question with the QR factorization one, I think I need to fix that up, but we'll see. We covered a lot today, okay? Okay, I think it was here. Okay, yeah, but this one was pretty cool though. This shows that there's 2 to the n unique QR factorizations. But I think I still need to fix this up. The result is still true, but there's a slight issue with the proof because proving D is orthogonal might be a bit more difficult than sequentially intended. So hopefully we'll fix that up before we upload the slides. But yeah, okay. Could have just done this the whole time. Okay. So yeah, to the non-existent audience, scan the QR code if you haven't. But yeah, thanks for coming, and we'll upload the slides soon, hopefully. And yeah, that should be it. Okay.